the idea of what the DFT is, let's review, just like write it out a couple of times so you can like have it kind of memorized or internalized, right? The DFT says the DFT as a function of frequency is some normalizing factor times I sum from n equals 0 to n minus 1, big N minus 1, of my signal multiplied by a complex exponential e to the minus j 2 pi k little n over big N. This can be interpreted as 1 over root n. Actually, to be honest, I don't even think this 1 over root n is in there in the product, but whatever. This can be interpreted again that x of k, the DFT, is maybe some constant times the inner product between x and the inner product between my signal. So this x here is little x of n, and this guy is ekn. Okay, that's what we talked about in the last video. If that doesn't make sense, go to the past video. Let's do an example. Let's find the DFT of a square pulse. Okay, and this one I'm actually cheating because we won't actually do the whole math out, but we'll just see how to set it up. So remember, square pulse of width m is, we're going to define it as 1 over root m if we are between, if we're before this m, and then it's 0 if we're bigger than this m. So again, that looks like this. Here's our m, and we look like this. Okay. Oh, sorry, we're discrete. So boom, here's our discrete stuff. That's not spaced out properly. Whatever, you get the idea. Okay, that's our signal. Let's find the DFT of it. So we literally plug into here, right? So what's that going to be? X of k is going to be 1 over root n times the sum from n equals 0 to n minus 1 of our signal. So the square pulse times e to the minus j 2 pi k n over n. As we've commonly done with the square pulse before, like when we calculated its energy, we also had this kind of sum behavior. Well, notice that after m, no one cares about it, right? And it's actually only till m minus 1. Technically, m should be 0. So this should be 0 here, and then this should be, 1 over root m. So we only care about going from n equals 0 to n equals m minus 1. So I'm just going to replace this sum. Instead of going from 0 to big N minus 1, which would be here, I'm going to go to big M minus 1. And then I can replace the signal itself, right? I can replace this signal itself with what the value actually is, which is 1 over root m. And then it's like, you can evaluate this. This is, I think you can literally just evaluate it the same way we did before, which is I like take this n out. Bro, this thing is not, okay, yeah, take this n out in a power like this, and then you have again, another geometric series. You can do something like that. Not as important, but this is what, if you were given a problem that says, hey, find the DFT of this function, this is how you would do it. And then you would just go about simplifying that sum. Okay. One more property of the DFT, an important one, is that the DFT is periodic. Okay. It's actually interesting, right? We obviously have periodic signals in like the signals we're dealing with, whether it's a square wave or a sinusoidal wave. Obviously in the time domain, these are periodic, but we're saying that even when you take the DFT and you look at, okay, instead of plotting against n, we're plotting against frequency, right? At a certain point, this DFT, maybe it might look like this, it's also going to be periodic, which is not obvious, right? That doesn't make a ton of sense. Like maybe you have some really high frequencies, but if you have a periodic signal, you'll also have a periodic DFT, and we can quickly prove that, and this will be an easy proof, and you'll see why. Our proof is to show, by the way, I'm going to say it's periodic with period equal to n. So I'm going to say every n, it repeats itself. So this would be 0, this would be big N, this would be 2n. It repeats itself. So let's prove that. So our goal is we want to show, WTS means want to show, big X of k equals big X of k plus n. So let's start with this guy. So big X of k plus n is going to be this normalizing thing, sum from n equals 0 to n minus 1 of x of n, little x of n e to the minus j 2 pi k, which is now k plus big N, n over n. And what we should notice is that we have already proved that for this guy, right? What is this guy? It's a complex exponential. Let's write it as let's write this as 1 over root n sum from n equals 0 to n minus 1 x of n e k n conjugate. We did that in the last video as well. I almost said last episode as if this was a TV show, but we did this in the last video as well. Now notice that we know that, sorry, not EKN. This should be E frequency K plus big N, N conjugate, correct? Because you just put a negative there, so that turns this guy into its conjugate. We know that blah, 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 EK plus N equals EKN. We proved that a while ago with the complex exponentials in the other unit. So basically we can say that this whole thing is equal to 1 over root n sum from n equals 0 to n minus 1. This x of n stays the same, and then this guy inside can turn into this guy. And then we can take the conjugate after. So x of n, sorry, this is very, very messy. X of n EKN conjugate. And then this guy is clearly just the DFT at x. Okay, so great, very nice. So DFT is periodic. That's actually very important. So again, that means that when we're looking at our DFT coefficient, so we'll look at x of 0, big X of 0, big X of 1, right? These are important. Like, I'll reiterate, this tells you how much of my signal is made up of frequency 0. This tells you how much of my signal is frequency 1, right? These are our spikes. So this would be x of 0, x of 1, x of 2, x of 3, etc. Okay. What this is saying is we only need to care about this many, because if I asked you about x of n, we can say, hey, x of n and x of 0 are going to be the same thing. So in terms of memory and storage, we only care about a finite number of components, which is nice. So we consider a set with n elements. Okay.